Let me start my presentation. First of all, thank you so much for Mary and the Remade project for giving me the opportunities to present our work uh, supported by the Remade project. And today I'm going to talk about one specific direction of the Remade supported uh, research about the recycling of aluminum-based material, in particular, how to using the extremely brilliant source, which is available in the Europe ESRF, to tracking the complex intermetallic phases in the recycled aluminum alloys, and how we're using some kind of low energy approach, green approach to change that detrimental phases in order to make the recycled aluminum more available for the industry. So, of course, this project has been funded partially by the Remade project, also by the European other different the resources from the ESIF and other synchrotron sources around the world. I'm particularly grateful for all my members, current and in past in my groups, for helping me to reach the current stage. So I'm currently at the University of Hull, which is just at this Humber estuary located facing to the North Sea. And I'm at the School of Engineering and Technology, director of the researcher in the school. And also I'm running this advanced material and manufacture research center. If you're interested, you can look at our website. So why this recycled aluminum is more important for this aluminum industry? Because currently we have, just for example, in the 2024, the primary aluminum production, just the global level, just reached 70 million tons. But actually, the global demand is around, over 100 million tons, and there's a demand gap around 29 or 30 million tons of the gap. So that means we need to use the existing material which is circulating in our industry, in our supply chain. And another second important issue is because the manufacture of the primary aluminum take a lot of energy. If you can use in the recycled aluminum, you can save 90% of energy during the melting process. Of course, that leads to a significant reduce of the greenhouse emission in this particular industry. So almost all the countries, all the let's say major manufacturing aluminum industry are trying to maximize the recycling capability and the rate of the secondary aluminum. Currently, only about less than 40% of the scrap circulating in our industry, in our supply chain was of the scrap aluminum was recycled. So there's a lot of long way to go in this direction. So what's the key issue in the recycled aluminum? One of those key things, because you have if you recycle the materials and through making cycles, you accumulate a lot of different let's say contaminations for those materials from different elements. Some of them, of course, are beneficial, but most of them, when you over a number of recycled, the element level will be exceeded to the design level of the normal alloy. So that will lead to a lot of detrimental, let's say, structure or phases or defect formed in the aluminum recycled materials. And among those, iron is probably the most common and most detrimental element almost in all commercial aluminum alloys, unless some are very special ones. And the iron is have very low solubilities in the solid state of the aluminum alloy, so they form a lot of different type iron containing intermetallic phases. If you look at some kind of example, I gave you something here, which is most of the iron intermetallic phases have very complex morphologies or shapes. Some of them are in just like the plain plate, which is like a knife cut into this matrix. That will be definitely some kind of stress concentration regime, which is it will damaging your mechanical properties. And also, in some cases, they form a very complicated, this kind of a convoluted network structures. Sometimes we call is so-called Chinese script type microstructure. You see, these are one typical things here. They start from the core here. There's core structure and branching out into in 3D space complicated, let's say, branching out structures. We will see in next few slides what it look like in the 3D morphology. But how we can find a way to understand how this is being formed and how this kind of what kind of effective measure we can use to change the structure and into the more beneficial morphology. And that's the key research agenda in many people involved in this type of research. Also part of my effort supported by the remade project here. So I'm going to show you some logical steps how we understand this kind of process, especially when in the liquid state, how this core was formed. When this core formed, how the branching out was growing, and in what kind of way is growing, and how we're going to change that growing. So I'm going to show you exactly from right start from the when we heat the liquid, the material into liquid state, and from the atomic level and the structural level, how this structure evolve. How this phase nucleate and grows and interplay with other different type of phases of structure. What particular technique we're using or is available for us to use to observe those kind of behavior in real time and in kind of a operational condition, which is mimic the industrial condition, manufacturing conditions. And what kind of effective measure support, for example, some kind of ultrasound-based method or magnetic-based method to implement it into this kind of material during the solidification process in order to change those structures. And I show you some a few very typical cases how we visualize these things and to enhance our understanding. So first, to start with the kind of the beam we're going to use or the light we're going to use, because we are working on metal-based materials, is a kind of a opaque, not transparent to the visible light. We have to use in some kind of a radiation light, let's say the X-ray or neutron-based other things. If you look at the this kind of evolution or development of the X-ray, of course, nowadays it starts from the beginning of 1900, and now we reach this state, which is the ESIF already have the first generation or the first of the fourth generation, so-called extreme brilliant source, which is currently at this level in terms of the brilliancy. The brilliancy means the definition of the fountain flux divided by the radiation angle by the radiation area on the 0.1% of the bandwidth. Of course, apart from this extreme brilliant source, we also now have some kind of free electron laser based source, which have a even much higher, let's say something like even 10 to 10 power in term higher in terms of the brilliancy. But that also is kind of a emerging technology, so we can use to apply it into the this type of research. But today I'm focused on the how we can use what I did using the extreme brilliant source at ESF, particularly in the beamline ID11 and ID19 to get the information we need. So if you have the X-ray, actually looking at the material is not extremely difficult. But what you need is, of course, you need to a way, because we're working on the metal materials. You need to find a way or some kind of arrangement or apparatus to heat up the materials, and that heater going to be portable to put into the beamline. And here to give you some example, you can have some metal sample holding on the container heated up by whatever the electrical resistor heating or inductor heating, and you have the materials, you shining the X-ray onto it, and any X-ray interaction with the material will be recorded on a detector. By analyze the information from the detector, you can extract the information about the atomic structure, about the nanostructure and the microstructure, so on and so forth. And this is a kind of a particular, some kind of spatial apparatus I used in the past 10 or 15 years. These are quite simple. This container is a coarse tube, which you can go up to high temperature without any issues. And we designed some kind of spatial furnaces and heated the material, the right shape, color these materials, and then we can kind of either just look at the material itself when it's cooling, or we can implement some kind of, in this case, is a vibration tape. Is a vibration here, which is can introduce ultrasound into the solidification melt, and that's some kind of a dynamic image about the cavitation due to the created by the ultrasound probe. We also have another particular equipment or apparatus which is similar to the heater, a similar size of a heater, but I can implement it some kind of magnetic field directly into this melt during the solidifications. The magnetic field can be continuous, can be like something like a very short pulse, and actually the magnetic flux is can reach peak magnetic flux can reach a quite high number here. And in the left is show you the particular cases of aluminum 15% nickel solidified under the pulsar magnetic field. If you're interested in more information, you can read this published paper here. So let's take a look of the atomic structure for molecular melt, and how that, when you're cooling down, how does atomic structure change and evolve and lead to the nucleation of different type of crystalline phases or intermetallic phases. So from X-ray radiography point of view, actually, if you have the correct X-ray, which is have the sufficient penetration power, sufficient flux, it's quite easy to look at the structure, look at the liquid materials. This is one case already solidified. And when it's cooling down, you just look at what's the phase is growing. And this is a particular aluminum to copper phase. And we watching this with the apply application of ultrasound on it without. But what we are more interested in here, just before any phase come out, the black one, how does the liquid structure evolve to form that kind of thing? And again, I use kind of adapt this furnace I have, which is have an X-ray coming shining onto the sample. The furnace have a window opened, which is allow the diffracted beam to be recorded onto the detector without blocking anything, without anything block it. And this is a sample. So you have the sample here. We put the thermocouple directly measure the temperature, and just immediately above the X-ray point, so you know exactly as this location how the structure change versus temperature. And this is some typical recorded data. This temperature design cooling curve. You have exactly the recorded temperature as you defined cooling rate, and then you watch at what point the diffraction spot are appeared. And before that, how this kind of a liquid structure evolved until the moment of the tiny diffraction spot appear. Of course, before any diffraction spot appears, you need some kind of other methods to work out the change of the liquid structure, because directly looking at the change of these a diffuse hollow ring can give you some quantitative information, but cannot give you 100% qualitative quantitative information. Only give you some semi qualitative information. So we have to kind of using the so-called total scattering method. In this case, it's particular for this alloy. That's the 4-element alloys, which is a composition particularly picked up for mimic the recycled aluminums. And we watch the change of this this intensity and versus temperature until you watch. Wow, there's a change of you see the slope of the peak, the first peak of the IQ, and then you can see the change of atomic structure, and until the suddenly there's a crystal phase appeared, which is have a peak come out right here. Using the standard method, we can of course index those different phases. But for the pre-nucleation atomic structure, we are mainly interested in this kind of regime. Just let's say the stratum here, just before you have a tiny crystal appear, and how this liquid structure change. As I said, by only looking at this IQ, we cannot give you some much more useful information. We have to kind of convert this kind of IQ versus temperature into the so-called structure factor and the Pyle distribution function using the Fourier transformation. When you have these, when you look at the Pyle distribution function, when you carefully looking at the change of the peak position, change of the peak height, and you can have quite detailed information. But in order to extract the atomic structure, we have using some kind of molecular dynamic based modeling to get that information. Here, we particularly interested using this so-called empirical potential structure refinement modeling method. Basically, it is some using the so-called reference potential and the empirical potential between different atoms to regulate the movement of between different atoms within the kind of simulation box until running this whole allow this the whole number of atoms in that box moving around until it's calculated PDF agreed with this experiment PDF. Such as this case, now we have the GR, the calculated PDF with the EPSR almost 100% match. And from that, we can extract information for the atomic structure. And this on the things on the right is show you the atomic structure with the atomic cluster in the liquid state with the iron atom in this particular alloy at the center. The reason we are interested in this, we wanted to work out what the role of the iron is playing in terms of nucleated the iron containing intermetallic phases. When we understand that, we can effectively implement some kind of methods to control that formation process. So using this EPSR method, we work out the liquid metal structure. In here, you see the complicated interconnection between the clusters with the iron at the center, and that kind of complex clusters connection together, which is, we believe, we find out this is the pre-nucleation atomic structure for these particular iron aluminum-3 iron phases, and how these kind of connection between the atomic structure evolve as the temperature is cooling down until reach this kind of this type almost approaching this crystalline structure of this type of phases with aluminum 13 iron 4, or in another simple word is aluminum 3 iron. Right? So we understand this now. Now we're using these the previous the diffraction. Of course, we're using the ID11 at ESF, and then we move on to the ID19 to look at after the nucleation, what's the phase growing dynamic looks like. In this particular alloy, we have a kind of a so complicated multiple phases. You look at the collected tomography data and shining through, and you see even just in a simple or the grid level construction, there's so many different things. So we're using the machine learning strategy to segment all the phases, and you can see we quite successful, so even segment the different type of iron containing phases through these slides. You can read the fully published paper on here. And by using this, we can now isolate this kind of a nucleated core, how it forms at a different temperature, and how the shape of the change from the global to some kind of a pyramid structure, and then at a different temperature, the different edges, edge or the point start to accelerate the growth, and those growths develop into a complicated network structure, and finally
I forget again today.
But form this kind of complicated, let's say, network structure, which is mimic this 2D structure here in conventional electron microscope. So we kind of almost fully understand this, how this kind of this iron intermetallic phase formed through the liquid state and to the solid state. And now, because we have fully characterized these starting from very tiny nuclei to the whole growing process, and then we now can fully understand how these look at this. This is how is a single core will develop it into the convoluted network structure, which we call the Chinese script type. And this is how the different phases can be growing on top of from other phases, and then collectively how the whatever you call the alpha phase or beta phase, how they look like in the whole volume of these structure of these materials. So we fully understand the process. Now we need to find a way to control this kind of a formation. And because these the phase were formed in the solidification process, we need to apply some kind of a control in this kind of a solidification process. So what kind of actual control we can do? In my research group, I have done a lot of ultrasound-based method, which is apply ultrasonic wave into the solidification melt or post-magnetic field. So give you some example here. So that's how we using the ultrasound, because ultrasound is vibration. So here you have a vibration tip here, and you have your material here. Because we're staining here, allow the X-rays penetrate to have a clear image. Because the ultrasound is vibration very fast, so we need the ultra fast X-rays. In the current situation, only the ESF at ID 19 and the APS at sector 32 IDB have these capabilities. Other synchrotron sources, of course, have a high-speed capability, but these two beam lines has the high speed up to a few 100,000 or even to million frames. So that's the most appropriate technique to do that. And it clearly can see the vibration of the tip. And we are more interested in understand the ultrasound capability when they transmit the sound wave into the mouth, how the sound wave changes structure, how the cavitation, look at this cavitation changes structure, how this kind of a strong streaming flow can change the structure. So that's the three fundamental issues when you're using ultrasound to processing any type of materials. So give you some example. These, if you have cavitation and you have a cavitation bubble, another bubble, let's say, growing and imploded, and that implosion clearly captured by the ultrasound, ultra-fast X-ray imaging. You look at when the bubble bursts. When the bubble bursts, at that moment, it will create when it bursts, it will create some kind of impact or shock wave. You see the velocity of the wall change. They have suddenly squeeze very quickly and then bend and reverse into direction. And this kind of momentum, when that bubbles acting on your materials, will create a very, very efficient way of structural fragmentation behavior. Give you some examples here. And if we look at some kind of without this particular phase growing without any ultrasound, is growing into a very long strip. If you have any ultrasounds, it can be quite effectively to break off the growing phases and breaking them off. Very, very effective. You can see that that's happening in few seconds. But these still you see the strong swirling flow. But if you look at any individual bubbles acting on your dendritic structure, you can see how efficient that vibration bubbles going to be break up you growing dendrite in just a few to a few tens of milliseconds. So, and you can see that kind of a vibration is so effective. Basically, this vibration we can use in some of the kind of fatigue model to understand how in how many ultrasound cycles those breakup happening, and then predict this kind of a fragmentation life. So that's already published on the paper. Interested reader can read those. And then this 2D version, and we also look at the 3D version where in the tomography setup at the TomoCAD of the Swiss light source, and you can see the this vibration tip. And at TomoCAD, of course, it cannot reach a very high speed in the tomography, but still you can see the quite strong swirling flow and acting on the green dendrite. By look at this circulating in the dendrite was fragmented in the swirling flow, and by looking at these carefully looking at the tomography data, you can see very, very clear with ultrasound and without ultrasound, this structure a quite different. Only just 5 to 7 second application of the ultrasound, the structure, dendritic structure with the ultrasound being refined at least something 50% less compared to the without ultrasound. So it's very, very effective. And we also look at this particular alloy. I showed you how we understand this liquid structure evolution before nucleation and after nucleation, how these different type of intermetallic iron containing intermetallic evolve. But when we apply the ultrasound in this particular alloy, and we did this again at the ID19, what is happening is shows very, very clearly without the ultrasound, that's the with ultrasound, that is the sum of one projection after the machine learning segmentation. You can see the effect on the dendritic structure. This is without ultrasound, and you can see the effect on the dendritic with the ultrasound. So the typically this dendritic structure was at least 50% of smaller. Also, the iron intermetallic phase was again at least something about at least 50% smaller. So it's very, very effective. You see the different distribution characteristic of those dendritic structure and those intermetallic phase. So we believe this ultrasound capability is the very important technique. It's very important. The technique can be explored in these in helping accelerate the recycling of aluminum. So I think the time is passing by quickly, so I gave you a summary. In terms of the ultrasound processing, there's 3 mechanisms can help to change the structure of the materials. One is including bubbles can create let's have local shock waves, so very effectively to fragment these growing phases in time scale of just a few microseconds. But the oscillation bubbles and also can produce a fatigue effect and can break off the dendrite and causing a phase of fragmentation. Again, this in a relatively longer time scale in tens of a millisecond. And the relatively stable acoustic swirling flow is acting on the much longer time scale, which is have it also have the similar effect, but it's acting on the structure in something like tens to a few hundred milliseconds. So that's the multiple scale issues, especially these occurred in different lengths of scale. We are able to capture with the brilliant this synchrotron source, in particular in the ID11 and ID19. So I think it's probably already half hours. So I stop here. If you have any questions, I'm happy to answer them. Once again, thank you for the organizer for giving me a chance to present the work.